So we were talking about the interstellar medium last time. It's basically all the matter, radiation, and even dark matter that exists in the space between the star systems in a galaxy. If you consider the baryons, then there is diffuse gas, mostly hydrogen and helium. Then there is dust. Dust means a solid phase entity. Uh, it could be iron grains, but it could also be silicate grains. Then there are cosmic rays of various energies from various sources like stars and AGN. Then there are, of course, magnetic fields there present within the ISM. They're very weak at the micro-Gauss level, but they're there. And then, of course, there's some amount of thermal and kinetic energy that is stored within all these particles and photons. And the ISM plays a crucial role in the formation and evolution of stars and galaxies. So what is it composed of? It's mostly hydrogen, maybe 70 to 80% hydrogen, 20-25% helium, and less than 1% metals. Okay. You can see this relative abundance of these elements is similar to the primordial composition of the universe, also quite similar to the composition of the sun at the present time. So over the last 10 billion years, so much energy has been generated, but only a small fraction of the primordial hydrogen has been converted to helium. Okay. And an even smaller fraction has been converted to these higher elements, which were not present at the time of the Big Bang. So it's a very slow process. The ISM can exist in various forms. The most densest ones we call molecular clouds. These are the regions in which stars are born. And unless you can form molecular clouds, you cannot reach high enough densities and pressures for fusion to ignite. So it is the fragmentation of these molecular clouds and collapse of those fragments that leads to the formation of stars. Then there are H2 regions, hot ionized regions around newly formed massive stars. Okay. Last time there was a question from one of you after the class, which asked is how can you get H alpha emission from ionized hydrogen? Okay, because H alpha we said is a 3-to-2 transition. So it's a sort of excited state to a lower state transition. And that does happen because the H alpha is coming from the ionized regions. But when you have an ionized region, doesn't mean everything is ionized, right? It means that some atoms are excited, some other atoms are excited more than others, and some atoms are ionized. That's what is there. There is a continuum of energy states of the hydrogen atom in the ionized cloud. So although we use H alpha as a tracer because it's a very commonly found emission line, more importantly, it lies in the optical band. And we have very sophisticated spectrographs attached to optical telescopes. So we can detect and measure that line very easily. So it's more a practical matter. It doesn't mean that H beta doesn't exist, okay? Or the Balmer limit doesn't exist, or the Lyman limit doesn't exist. It's just that those are more inaccessible to us. That's why it's when we say H2 regions, these are ionized regions, and they are also traced by the H alpha emission. There are diffuse clouds. These are your atomic gas containing clouds, and these can be traced via the H1 line, which is at about 21 centimeters or at about 1420 megahertz. Then there is coronal gas, hot diffuse gas at millions of Kelvin. This is mostly in the regions surrounding the AGN itself. So the AGN is producing so much energy. So just like the sun has a hot corona that surrounds it, AGN also have a hot corona that surrounds them. And like with the sun, it's very low density gas, but it's at very high temperatures as measured by their by their mean velocities. Dust grains are there. These are small solid particles of ice and carbon-rich material mostly, and occasionally you have iron grains, okay? But not always. So why is the study of the ISM important? It basically provides the raw material for star formation, because stars form from gas, and the gas is initially all in the ISM, and it has to somehow come together in one place to form the stars. It regulates the evolution of galaxies, because the ISM can be a storehouse of energy, essentially, or it can be a storehouse of matter as well. Therefore, the evolution of galaxies is affected by the pressure, density, temperature of the ISM. It contributes to the magnetic field structure of a galaxy. Okay, there are magnetic fields in the ISM. And cosmic rays, of course, propagate through the ISM. They generate their own emission. And it also absorbs and scatters starlight, and this affects our observations. So if you're observing through a dense part of the interstellar medium, then your observations will be strongly affected. So whether you're studying stars, whether you're studying galaxies, external galaxies, understanding the properties of the ISM is quite important. So how do you study the ISM? Various techniques are used today. Emission lines. So there are atoms and molecules in the ISM. They get, once photon impinge on them, they can get excited. They go to the excited state, and then they jump back to a lower state, and they produce emission lines. If they are primarily absorbing, then the photons from some background source can be absorbed by our atoms and molecules. This will produce absorption lines. The dust grains are at don't show too many lines, but what they show is continuum emission, thermal emission coming mostly in the infrared and submillimeter bands. Why does it come in infrared and submillimeter bands? Why not at optical bands or infrared bands? Huh? No, but this is mostly thermal emission. There is also rotational lines and all are there, but you're right about that. But this is continuum emission. They absorb optical light and they emit in the infrared. So what does that tell you about their temperature? If something is emitting thermally with a peak in the submillimeter, what does that tell you? Huh? 300 Kelvin will peak at about 10 microns. Okay. So if you wanted to peak at, say, 100 microns or 500 microns, it is much colder. 100 microns, that dust grain will have a temperature of 30 Kelvin. Okay. So it's very cold dust, which is emitting at longer wavelengths. And that is easy to understand, because look at the solar system. Up to the Earth, already the temperature has dropped to 300 Kelvin, the equilibrium temperature. By the time you go to Jupiter and beyond, it's quite cold. So any dust that is present even within our solar system is bound to be quite cold. If it is outside the solar system, say in the Oort cloud or even beyond that, it's going to be very cold. And that is why the emission is at very long wavelengths. Now, these cosmic rays which are there, they lead to radio emission. Okay, and spectral lines from molecules. So, for example, the OH ion is very, very common in the universe, and that creates lines, spectral lines, which can be observed with the radio telescopes. So then, of course, carbon monoxide and other such molecules are also there, which show transitions. And these are the kind of rotational transitions that you were talking about. So that comes mostly in submillimeter and radio, right? Polarization. So this is very interesting, that the alignment of dust grains due to the magnetic field can polarize the light that is passing through the interstellar medium. If the dust grains are all aligned in a particular direction, then the radiation that passes through that iron-rich dust cloud, that is going to get polarized. And these kind of measurements have been made. They're of course very difficult to make, but they have been made. So there are a lot of challenges in studying the ISM. First of all, it's extremely tenuous, very low density on average. It's also highly inhomogeneous. So there is a very wide range of temperatures, densities, chemical compositions. So if you take the ISM and the IGM, the intergalactic medium, what do you think will be systematically different between the two? Will the chemical composition be different? No reason. This is mostly hydrogen, that will also be mostly hydrogen. What can you say about the temperature and pressure in ISM versus IGM? Where will it be higher? ISM, correct, right? So ISM has significantly higher temperature, significantly higher pressure, significantly higher density than the IGM. Okay, but the volume of the IGM is very much larger than the volume of the ISM. So if you ask the total amount of hydrogen, where does it sit? So it actually sits in the IGM. The maximum hydrogen sits in the IGM, but it's at the lowest density. Right. Another problem with studying the ISM or the IGM is that the relevant physical processes, turbulence, magnetic fields, cosmic rays, all of these are very poorly understood. Okay, some of it is like sort of inherent. I mean, turbulence, you know that turbulence is not something which can be easily written down in simple equations like electromagnetic theory and so on. It's a very complicated process, often requires numerical modeling and solution of systems of coupled differential equations. I mean, the whole thing is very, very complex. Anything to do with the fluid is very complex. Magnetic fields are also very complex to handle because they're very difficult to measure. If we had just had a map of the magnetic field everywhere, we could have built a much better model, but we don't know what it is. Cosmic rays span a very large range of energies. So although we understand the physics of cosmic rays quite well, we don't really understand the number and the energy distribution of cosmic rays. So maybe that's a problem that can potentially be solved. And then if you're studying the ISM, there can be stuff in the foreground, there can be stuff in the background that can complicate your analysis. And modeling the ISM requires complex computer simulations that incorporate many different physical processes. Okay? And of course, overcoming these challenges is quite crucial. And the last point, modeling the ISM requires complex computer simulations. So one big example of such a simulation, is a code known as Cloudy. It's a spectral synthesis code which is used to model interstellar clouds and predict their emitted spectra. So what Cloudy does is that if you tell it that there are so many clouds, this is the temperature of each cloud, this is the density of each cloud, this is the distance to each cloud, etc., etc. It will build for you, it will predict for you what is the kind of spectrum that you will get. You'll also have to give it the chemical composition so that it knows which lines to include, which lines to not include, and so on. So it can model any kind of plasma, H2 regions, planetary nebulae, active galactic nuclei, hot intracluster medium, everything. The code uses a database of fundamental data. And these fundamental data are some lab measurements which are continually improved over time to improve the modeling treatment of these microphysical processes. There is a file within that, within Cloudy, which is called Cloudy Lines. It's a file that contains data on the nebular line emission produced by the interaction of the stellar radiation field with the interstellar medium. And it's widely used in the analysis and interpretation of emission line spectra. And thousands of scientific papers have cited the Cloudy code. And it has been in continuous development since 1978 and throughout by just one man, Gary Furland, who's a professor, I think, at the University of Kentucky. And he started developing Cloudy when he was a PhD student. And now he's an emeritus professor and he's still developing Cloudy. So it really, for me, this is one of the codes in astrophysics that is like just amazing, that one man working steadily for 40-45 years can achieve so much. So if you end up working on IGM or ISM during your PhD, you will surely encounter this code. Yeah. Yes. The stellar corona is quite weak, okay, compared to the corona of the AGN. So much of it will come, contribution will come from the corona of AGN. And I don't know whether one should consider the corona of the sun as the ISM or not. It is so close to the sun, it's practically a part of the sun, right? It's like the outer atmosphere of the sun. It's not really ISM. But in the case of AGN, it can be really far away. It can be many light years away. But the AGN is so powerful that it can energize gas clouds which are quite far away, many light years away. Right. Okay. So metallicity and how it evolves with time, this is very simple. It evolves monotonically because metals can only, because of our fusion processes, metals can only be created. They cannot be destroyed. So from the first second of the universe's existence, this is a monotonically increasing or at least non-decreasing function. Continuously metals get produced and the metallicity increases. And initially metals get produced in these population 3 stars, right? And the most massive amongst them die. The low mass ones are probably still alive. We call them population 2 stars. And they are produced metals. Population 3 stars were interesting because all of the massive ones went supernovae. And they created a lot of metals in the early universe. And not only did they create the metals, they didn't keep it with themselves. They scattered the metals into the interstellar medium. And then the next generation of stars were born, like population 1 stars, like the sun, were born from these, from the polluted interstellar medium from population 3 objects. So that's how metallicity evolves in the ISM. So this is an image of the Carina Nebula with the James Webb Space Telescope. This was one of the early release, the first images that were released from this particular telescope. It's very interesting in many ways. First of all, I mean, if you imagine what this image would have looked like if observed with the Hubble Space Telescope, what do you think would have happened? So let me give you a hint. There is some star here, there is a dust, this sort of dark brown or black and brown region is a dust cloud. There is a star which has been born in that cloud. And that star is basically radiating a lot of energies. And that energy those impinging photons coming from the upper side are eating away that dust cloud. And the dust cloud is slowly getting destroyed. So if you had observed this same part of the sky with Hubble Space Telescope, what would you have seen? What would be the difference basically? Sorry, dust? Dust will do what? Yeah, that's correct. So the dust will block most of the light that's coming from here. So here we can see even in the most dusty regions, we can see some stars, right? They are either embedded in the dust or they're behind the dust. In the case of the HST image, you would not see these stars at all. You may see some of the stars here which are in the low dust region, but all the stars in the highly dusty region, you will not see at all. Okay. That would be the main difference. So that is the complementarity. In here, you can see the dust. It's the hottest dust is already emitting quite strongly. And the little bit less hot dust is not emitting as strongly. So the dust has not become fully transparent, okay, but it has at least become easier to see through here. So needless to say, the ISM is the most beautiful part of the universe. So all planetary nebulae, they are ISM. They form very, very beautiful structures. You might have seen them. This is a nebula. This is another nebula, which is called as the Eagle Nebula. This is the most famous image taken with the Hubble Space Telescope. And people have used it on music CD covers, to make T-shirts, to make mugs, and so on. The good thing about these things is that all the NASA images are sort of almost public domain. So you can use them to create your own calendars or any other piece of art. So this is the most downloaded, most widely used image obtained with the Hubble Space Telescope. And here again, the same thing is happening. There is a star on top somewhere here, which is actually, see this illumination of the edge, that is starlight that is falling onto that. And that is slowly eating away this dust cloud. And this dust cloud happens to have a sort of higher density along these columns. So that's why these columns have survived. But the lower density regions between the columns have been all eaten away and destroyed. So many people work on the ISM. They are trying to understand all of these unknown things. Okay. They're also exploring the role of the ISM in the formation and evolution of all these stars, planets, and galaxies. They're studying cosmic rays, and they're developing more and more sophisticated models and simulations to represent or model the interstellar medium. And they're using new observational techniques to study the ISM in greater detail. When we talk about high redshift galaxies, I will come back a little bit to this topic, but in the context of the intergalactic medium. And there we will look at some new observational techniques and technologies to study the IGM in some detail. Okay, so we have now covered many of the topics that we want to cover. So I thought this is a good time to flash this slide. So what I've done is I have tried to collect together the research areas of IUCAA and NCRA faculty. And there are of the order of 35 people who are faculty members at one of these two institutions. And you can see that ranging from sun to quantum technologies, the research interests span a fairly wide range. Okay, some things like stars are quite underrepresented. Planets, I put down Surud, but really this is not his main business. But he has a project where he's looking for this Planet 9 thing, something beyond Neptune. So I put him down there, but his main work is in weak lensing and cosmology. Compact objects are very popular here because in NCRA there are lots of people who study pulsars, and so neutron stars particularly. So the study of neutron stars is a big industry at NCRA. Studies of the interstellar medium and the intergalactic medium is also quite popular. There are people both at IUCAA and NCRA. Sri Anand has been working on the intergalactic medium for many decades now. Galaxies, of course, there are several of us who work on that. Galaxy clusters is a bit underrepresented, but Ruta Kale at NCRA, she studies radio clusters. AGN, again, this is a fairly popular activity. Some people are study AGN in the radio. Some people study AGN with using X-ray data, like Gulab or Ranjiv. There are people who do modeling of AGN jets, like Dipanjan Mukherjee. Many of the NCRA people are doing AGN studies in the radio. Then gravitational waves. Okay. Sanjit, Debarati, Shashwat, these people are quite active. And of course, in IUCAA in the past, people like Dhurandhar and others, they were also quite active in the study of gravitational waves. Observational cosmology. So this is sort of the early universe or high redshift universe and so on. Surud, Asim, and Tirthankar at NCRA. Instrumentation development, Shubhadeep actually also falls into that category, but mainly led by Ram Prakash at IUCAA. And Shubhadeep is working on some new quantum technologies, which are becoming increasingly important because it's also well supported by the quantum mission of the Indian government. Okay. So some months ago, I found this interesting periodic table representation, which tells you where are the elements synthesized. Okay, and the color codes are there. So you can see that hydrogen, for example, is entirely primordial, right? There is no hydrogen, no new hydrogen can be produced. But so much was produced in the beginning that we are still dominated by hydrogen. Helium is mostly in that category, also mostly primordial, but there is helium being let out into the interstellar medium. So this is, I think, the composition of metals in the interstellar medium. So there's lots of helium in the interstellar medium. Most of it is primordial, and small amounts of exploding stars, both low mass stars and high mass stars, which have shed their matter, have contributed to the helium in the interstellar medium. If you go further down, then the relative composition changes. Okay, so for example, carbon and nitrogen are coming both mostly from low mass stars and a little bit from massive stars, whereas many of these elements are coming from exploding massive stars. What is new, meaning new in the last decade or so, there is increasing evidence that the elements which are sort of predominantly purple or magenta in color, these elements were synthesized in merging neutron stars. Okay, so modeling has revealed that probably these elements came mostly from neutron stars. A little bit of it may have come from dying low mass stars or exploding high mass stars. And of course, these elements don't exist in the universe. These are sort of human synthesis, no stable isotopes, they quickly decay. So we I mean, this tells you that how much essentially what we are and everything around us has been synthesized inside stars, and much of it in this dying phase of stars. So it is the dying phase of stars that leads to the production of all the higher elements, supernovae and things like that. 43. This is molybdenum, rubidium. What is this? Tc. I don't know. This looks strange, no? It's colored like this, huh? 61 is also. So maybe these things, the higher elements one can understand. This is the lanthanum series, actinium series. They're all pretty unstable. So if there are no stable isotopes, so if the half-life is very short, then they may not exist in large quantities in the real universe. So this is rhodium, this is rubidium. I have to check what this is. It's clearly because it's not coming to mind. Obviously, it's a very uncommon element, but we can look at that. So atomic number 43. Right. So just wanted to mention that there is, which are the elements that formed during the Big Bang? Hydrogen, helium, and a little bit of lithium. Okay, nothing else formed during the Big Bang. Everything else formed later on. Okay, so let me see if this works. Okay, so now we change gears and we begin to talk about galaxies. Okay, and I wanted to show this video to start with. So if you look at the title, stellar orbits around the galactic center. So what is now possible to do by observing stars over many decades using the Keck telescope is to actually track the motion of stars around the center of our galaxy. And what do you notice happening? What's happening with the stars? That's the date, by the way. Okay. So these are going around the center of our galaxy. These are in orbit around the Milky Way black hole. So that already tells you there's a black hole at the center of the Milky Way. Because the stars, when they approach the center, they speed up. Okay, so now we will talk about galaxies for the next couple of lectures. Galaxies are a very active field of research today. If you take, I just counted all the papers, refereed papers in 2023. 32% had the word galaxies in either the keyword or the abstract. Okay. So there were 9,287 papers in 2023 alone. Okay. So 9,000 papers. So if you say I will work 300 days a year, okay, even then you will have to read 30 papers a day to keep up with the refereed literature. This does not include papers presented at conferences and things like that. that is unrefereed. Okay? Just the refereed literature is 9,000 papers. Each paper is on average about 10 pages long. You will have to read 90,000 pages a year just to keep up with the literature. So you can imagine the scale of the effort just can't be done. But because it's the good thing about this is that because so many papers are being written, new ideas come up, they are debated, they are discussed, they're refuted, they're accepted, everything happens pretty quickly. And when we talk about high redshift galaxies, I'll give you examples of how the James Webb Space Telescope has radically altered our understanding of high redshift galaxies. So most things about galaxies that we will study here were discovered in the last 25 years. It is changing so rapidly. Okay, so why are galaxies important? They're important in the same sense that atoms and stars are important. Atoms are important because they're the basic building blocks of everything. And in order to understand stars, the properties of stars, you have to understand the properties of atoms because they are undergoing fusion, they're getting ionized, plasma, everything. Similarly, in order to understand galaxies, you need to understand the properties of the stars that constitute them. So that is why we studied stars in great detail, so that when we talk of galaxies, we talk of galaxies as agglomerations of stars. And the properties of galaxies will be the weighted average of the properties of the constituent stars. And why are galaxies themselves important? Why do we study galaxies? They are the building blocks of the universe. So if you want to understand the structure of the universe on the largest scales, and we call it descriptively large scale structure of the universe. So if you want to understand the large scale structure of the universe, then you have to understand the properties of galaxies, because the galaxies can be treated in the large scale structure of the universe. You're talking of boxes 100 gigaparsecs across. So on those scales, the galaxies can be treated like particles. Okay? So therefore, we study galaxies because galaxies allows us to study large scale structure, and large scale structure is something that is of interest to people who do cosmology. So cosmologists want to have their theories predict some structure on larger scales. And if your observations match their predictions, then you say, okay, this theory is likely to be correct. We'll go very quickly over the history of the study of galaxies, and it's very sort of discontinuous. In 1755, there is a book called the General Natural, book was written called General Natural History and Theory of the Heavens by a man named a philosopher, not even a scientist or a physicist, called Immanuel Kant. And he said that the Milky Way is like a huge solar system. It's rotating, and its origin is from a rotating cloud. And the stars far from the disk plane are on different orbits. Disks like the Milky Way project to ellipses. So they're inherently circular, but if you look at them at an inclination, they will look elliptical. And oval nebulae, seen at that time by an astronomer called D. Maupertuis, he said they were island universes, which means they were outside our galaxy. They were like different things. I always wonder how this man could have written all of these things down. Okay, but it is possible that many people wrote many things down. This fellow got it right, and so we remember him. But really, it's quite remarkable that in 1755, he had no scientific information on any of these things, but he wrote it down in a book. Okay, so that was 1755. And in 1912, when spectroscopy was just starting out, an astronomer named Slipher discovered that some of the nebulae are rotating. So these were actually spiral galaxies. And at that time, they used to call everything as a nebula. So spiral nebula, elliptical nebula, and so on. because the consensus was that galaxy is very big and there's no way there can be anything outside our galaxy. Our galaxy is the whole universe as it exists. So in 1920, there was a debate organized in Pasadena in California, which is known as the Shapley-Curtis debate. And the question asked in the debate was, are spiral nebulae island universes? The island universes that can't talk about. And Shapley said no. Curtis said yes. They are island universes. They are outside external galaxies. And each of the debaters had to make a 30-minute presentation in support of their hypothesis. And then at the end of it, there was a vote, like who has won the debate. And Shapley won the debate. And these were not some ordinary people. These were some of the finest astronomers of that time who were there in the audience. Because this Mount Wilson Observatory had the biggest telescope in the world and so on. Shapley won the debate, although Curtis was right. But only a few years later, Hubble discovered Cepheids in the Andromeda galaxy. He used that to find the distance, and he showed that there's no way Andromeda galaxy is sitting inside Milky Way. It's very far away. And you can regard this discovery as the birth of extragalactic astronomy. And so this whole field is less than 100 years old. Next year, we can have its centenary celebration. Okay, so what are galaxies? They're gravitationally bound agglomerations of stars, dust, gas, and dark matter, right? So just like the ISM was basically dust, gas, and dark matter, galaxies are ISM plus stars. Mass ratio of dust to gas to stars to dark matter, on average, remember it can vary from galaxy to galaxy. It's not a constant, but if you just average over all galaxies, then the mass in dust is, if it's 1, then 10 times more gas, 100 times more stars, and 1,000 times dark matter. So dark matter dominates in terms of mass, then stars, then gas, then dust. This is within galaxies. If you go outside galaxies, what will dominate? If you go to the IGM, dark matter will still dominate. Okay, don't bring dark energy. I will just talk about matter at the moment. Dark matter will still dominate, but what will be the second most component? Gas. Okay, stars will be 0. Dust will be also nearly 0. It will be primarily dark matter and gas. Right. They are the building blocks of the universe on the largest scales. They show a broad range in their physical properties. And understanding the details of galaxy formation and evolution is one of the main outstanding problems in modern astrophysics. There are plenty of galaxies. There are 10 raised to 11 galaxies in the observable universe. And they range in mass within these ranges. Most of the galaxies will be within this range. There will be a handful of outliers who will go out on either direction. This is stellar mass. This is the stellar mass. I should probably put it there. No, sorry. This is not stellar mass. This is the total mass, including the dark matter. Yeah. So, although we didn't know galaxies existed as external objects, already in the 1700s, Messier made a catalog of 109 nebulae so that comet hunters wouldn't mistake them for comets. And about 40 of these were galaxies. And then there was more than 100 years, 130 years back, there was this NGC catalog that was produced. It had 7,800 objects. About half of them were galaxies. The other half were nebulae and other things. In the 20th century, many catalogs were produced. These were mostly galaxies. And now we have automated surveys with tens to hundreds of millions of galaxies. And the next generation surveys will have billions of galaxies. So for example, the Rubin LSST survey, which will start hopefully by the end of next year, is expected to detect 20 billion, billion with a B, 20 billion galaxies in its survey. So in any kind of study, first step, you just measure how many objects there are, then you try to classify them. And third step is understanding. Okay, try to understand them. So as far as classifying is concerned, Edwin Hubble proposed a scheme for classifying galaxies. It's called the tuning fork diagram. And he first presented it in his 1936 book, The Realm of the Nebulae. And this scheme survives in its essence to the present day. And it says that galaxies come in basically 4 different flavors. Okay, there are ellipticals, there are lenticulars, there are spirals, and then there are irregulars. These are the 4 kinds. Okay, a better approach from hindsight may be to look at the properties of subsystems within galaxies, disks, spheroids, halos, etc., and deduce their origin and evolution separately. So we will encounter all of these terms in the coming slides. Classification is useful because they include the majority of galaxies, and it's quite unambiguous and easily identified criteria can be used in this classification. And perhaps most importantly, they actually correlate with the physical properties of the galaxy. So if you see an elliptical galaxy, already you have some insight onto its physical properties. If you see a spiral galaxy, already you know a little bit about what its properties are likely to be. Into their internal processes, their formation and evolution. Okay, so why do we classify galaxies in the optical band? So historically, of course, optical photometry was the only way to observe galaxies. Also, Hubble's classification is most widely used. But in modern times, other criteria like color indices, spectroscopic parameters, the broadband spectral energy distribution. For example, you might say that galaxies with or without radio and or X-ray emission. So you can have X-ray galaxies and radio galaxies and so on. They are also used to group similar galaxies together and to study their properties. So for example, the study of radio galaxies is a major activity at NCRA. Okay, so this is the Hubble tuning fork diagram. Okay, so what do you see here? So over here, you see a perfectly spherical elliptical galaxy. So it appears like a circular object in projection. So that is called as a E0 galaxy. And as you go downwards, the numbers increase and it becomes more and more elliptical. E7, E8, E9, those are the most elliptical. Then you come to the base of the fork, and you have here something known as a S0 galaxy. So S0, these are the so-called lenticular galaxies. And then so you know what lenticular means? You know what that shape is? Have you ever seen a tur dal, whole tur or moong dal kind of grain, right? There are 2 halves, right? And they fit on each other, right? So they're not spherical, they are slightly elliptical, and they can be stretched near the center. So in this case, they're stretched because they have a disc-like structure. Beyond the base, there are 2 arms of the tuning fork. Along one arm, you have these spiral galaxies. So these are what are called the unbarred spiral galaxies, SA, SB, SC, and so on. Below you have the barred spiral galaxies because they have bar-like structure. So there is a sort of central structure. This is not very clear. I'll show you examples of barred spirals. And then, of course, there are these irregular galaxies which don't fit into this structure at all because they have just some random shape. Now, this diagram is not as important as the Hertzsprung-Russell diagram because it's not so tight, but it is still very useful, and we will keep coming back to this diagram or variants of this diagram when we study galaxies. Okay, so first, elliptical galaxies. About 20% of field galaxies are ellipticals, but most ellipticals are in clusters. So what is meant by field? So I should probably explain that. Field galaxy means a galaxy that is not surrounded, does not have any close neighbors. That's called a field galaxy. Then you have, at higher galaxy density, you have something known as galaxy groups. So where you might have 2, 3, 4 big galaxies and lots of maybe 20, 30 smaller galaxies. The Milky Way is part of a group. We call that as the local group. So the Milky Way sits in a group. Why? Because it has Andromeda galaxy and one more galaxy known as the Triangulum galaxy. These two galaxies are reasonably big galaxies and they are neighbors of the Milky Way. And then there are a bunch of dwarf galaxies, small galaxies, which are part of the local group. So that's the second structure. The third structure is galaxy cluster. Galaxy cluster means there won't be 20, 30 galaxies in it. There will be several hundred, 200 galaxies, 400 galaxies, 500 galaxies, maybe even 1,000 galaxies. So that is called as a galaxy cluster. So that is, of course, the highest density of galaxies that you can have. You can also have larger structures which are called superclusters, but those are very rare and they are not gravitationally bound. The largest gravitationally bound structure in the universe are galaxy clusters. Okay. So there are two nearby clusters which you might hear about frequently. One is the Virgo cluster and one is the Coma cluster. The Virgo cluster is relatively nearby, but it's less massive. Coma cluster is really a very big cluster. It's a little bit further away. Okay. So ellipticals, 20% of field galaxies are ellipticals. But most ellipticals are in clusters. And we'll see later why ellipticals are more common in clusters than in the field. There are a number of different subtypes. Okay, there are normal ellipticals, which we already encountered on that tuning fork diagram. Then there are what are called CD galaxies. These are massive bright ellipticals at the centers of galaxy clusters. So these are a little bit different from the field ellipticals, okay, in their properties, and therefore they are labeled differently, Ds. Then there are what are called dwarf ellipticals, okay, and then there are what are called dwarf spheroidals. When we talk of dwarf galaxies, we will look at these in a little more detail. They're smooth and almost featureless, no spiral arms, no dust lanes, and they are generally lacking in cool gas, and therefore they cannot form stars. So they have very few young stars. They have lots of old stars, but they don't have any recent star formation. Elliptical galaxies are denoted En, where B by A is equal to 1 minus n by 10. An E4 galaxy, therefore, has an axis ratio of B by A of 0.6. And E0s have circular isopods. They're perfectly spherical objects. So this is what a typical elliptical galaxy will look like. And this kind of color in the optical is characteristic of this sort of yellowish color is characteristic of galaxies that are not forming stars at the present time. They have very few young stars. All the stars are old. They're smooth. They're featureless, egg-shaped objects, which also evolve very slowly. So it'll take billions of years for them to change their size, shape, and character. They'll just keep shining like that. Lenticulars are characterized by the presence of a central bulge. So this kind of sort of spheroidal structure that you see in the elliptical galaxy, the whole elliptical galaxy is what is called as a bulge. It's a three-dimensional structure. So if you want, if it helps, you can think of an egg-shaped structure, three-dimensional, of a certain size. That's the bulge of the elliptical. And the elliptical has nothing else. So it's like 100% bulge. Lenticular galaxies, on the other hand, are characterized by the presence of a central bulge. So they have a bulge like elliptical, but they're not 100% bulge. They have a disk also, but they don't have any spiral arms. So in some ways, they are like spirals because they have a disk. But in some ways, they are like ellipticals because they have a bulge. In some ways, they are like spirals in the sense that they have some gas. In some ways, they're not like spirals, meaning they have some gas, but their star formation rate is not as high as spirals. It is more like ellipticals. So in many of their properties, these lenticular galaxies are intermediate between ellipticals and spirals. So this is an example of a lenticular galaxy. This whitish region is the bulge, and this sort of dark brown region is the disk. Okay, this disk has a lot of dust, and that is why that dust absorption is producing those bands. And the disk is edge on, so it is appearing like a straight line kind of. If it were face on, it would appear